All right, this should be our sixth and final part of chapter 20. I told you this one was going to be a doozy. So we still have two more functional groups. We have the amides, which are appropriately at the end. They're the least reactive. We're not going to have as many reactions. And the nitriles. So let's jump in. We're looking at that amide reaction. Now, preparation of is mostly just review. Preparing an amide, right, we just learned that we can do through aminolysis. So you could start with an acid halide. You could start with an anhydride. It's not the best, but you could even start with an ester. And you can treat with ammonia or a primary or secondary amine, and then you can make an amide. We've already covered those. We've looked at the mechanisms for them. You are already responsible for those. So, low battery. So we can just jump right in to the reactions of amides. Now, this should be unsurprising. It's a new reaction, but is it really? It's hydrolysis. Oh, well, there we go. Here we go. Hydrolysis, just like we have seen with the halides, the anhydrides, the esters. If you treat this with water, and in this case you do need the acid, so let's make that H3O plus. Again, because this is not as reactive as these first two groups, you need that acid to help make it more reactive, just like with the ester. But then the water can attack, and you can make a carboxylic acid. You'll also get some amine ions or aminium ion, not aminium, sorry, ammonia or ammonia-like ions. This mechanism you should be able to do. Again, I'm just going to start it off for you here. You're going to have to protonate first, right? After you protonate, I guess I should finish that. There we go. NH2. Now this is more reactive and water can attack. All right, and then you can continue that on. You know that you're going to have to deprotonate the H2O that adds. You're going to have to add a proton to the nitrogen to make it a better leaving group. All right, this is one that you can practice on your own. All right, it's slow. It requires high temperatures, but it can be done. All right, it's one of the reasons that we see amides in nature more frequently is because they don't fall apart that easily, but this is a reaction with some heat and some patience. You can get to work. If you didn't want to practice it on your own, of course, Klein has your back. It can also be hydrolyzed under basic conditions, just like with the ester, right? But it's even slower than acidic conditions, and so I'm not going to present this one to you. Very, very simple, basic mechanism, but you're not going to be responsible for it, so we're going to continue forward. Reductions. Now, this is important. You're not going to need to do the mechanism, but this is going to be different from the reductions we have seen previously. You're still using LAH. You still need an excess amount. You still need to work it up with water. It still needs to be a 1 and a 2 step. None of that has changed. The thing that is different is you are not making an alcohol. You are making an amine. All right, so if you have a nitrogen in your functional group when you go to reduce it, you are going to make an amine instead of an alcohol. I don't know how to emphasize this more. Bright, flashy lights. This is an easy reaction, but it is a little bit different than what you've seen before because it's making an amine instead of an alcohol. And that's it for amides, right? It's short. It doesn't do a lot. You can hydrolyze them with some pressure. You can reduce them. You really can't do much else with them, at least nothing that we're going to approach in this chapter. We're going to finish off talking about nitriles, but in case any of you are still here and have made it this far, I want to tell you my favorite joke. And this will give you too much insight into me, but here we go. What do you call a fish with no eyes? Okay. I don't know. I'm sorry. That always makes me super happy, and so I wanted to share it. All right. Now, nitriles. This is our last and final functional group in this giant chapter of insanity. You can treat an alkyl halide with sodium cyanide, and you can make a nitrile. You learned this in Organic 1. We reviewed it a few slides. We've reviewed it a couple times over the year of organic. This is not a new reaction. You can easily, through an SN2 reaction, replace a halogen with a CN. Now, if you're going to use this synthetically, it is important that you recognize this extends the carbon chain by 1. One of the most common mistakes when people use this in synthesis is that they use too many carbons in this piece, and because they forget that the nitrile does extend that carbon chain. So always make sure that you are paying attention to that carbon count. Now, there is another preparation reaction that you need to know. So this one was review, and this one's going to be new. If you can make an amide, and I know you can make an amide because I just taught you how to make an amide. If you treat this with SOCl2, yes, we saw this earlier in the chapter. SOCl2, or thionyl chloride, can take an amide to a nitrile. The carbonyl carbon becomes the nitrile carbon. SOCl2, if you remember, you did see it before, right? If you have a carboxylic acid, you treat with SOCl2, you can make an acid halide. It is useful for both. You don't have to know the mechanism of either, but you do need to be able to predict the products. I will ask you these. They will be useful in synthesis. So you do need to know all three of these reactions. This was just a random review one that I wanted to show you. This is actually pertinent to this section. Now, you do not need to know this fun mechanism. I know this is going to surprise you, but you can hydrolyze. Even though it looks different, the nitrile, when treated with H3O plus and heat, will hydrolyze all the way to a carboxylic acid. Yes, it will go through an amide intermediate, but you're not going to be able to necessarily control this. It's slow, so perhaps you could, but you would ultimately what you would want to do in these conditions is go all the way to that carboxylic acid. I'm not going to ask you for the mechanism of this reaction, but again, you are responsible for product prediction. It is analogous to the mechanisms we've seen before, but it does look a little bit different because you have a nitrile instead of a carbonyl. So I'm not going to ask you. There's enough mechanisms that I will give you a little bit of a breather on that one. It can be hydrolyzed under basic conditions. I am going to stick to acidic conditions. So you do not need to commit this to memory, this slide here, 97. If I'm not going to ask you to know the reaction, I'm certainly not going to ask you to do the mechanism. Grignards. This is another one that's interesting. it is a reaction that you have seen for ages. This is the most different application of the Grignard that you're going to see because you're actually going to stop with a ketone. You have your nitrile. The reagents look the same as any other Grignard you have seen before. You are going to work up with a second step of water or H3O+. Right? None of that changes. But in this case, you are actually going to stop at a ketone, right, where you add the R group from the magnesium. Again, you want to make sure that you're counting your carbons. This nitrile carbon is your carbonyl carbon. The reason it stops at the ketone is because it actually makes an aminium ion first, which is not reactive to the Grignard, and the H3O+ comes in and hydrolyzes it to the ketone. So it is a very different mechanism. I'm not going to ask you for it, but that's the explanation for why this is the only Grignard you've seen so far that does not result in an alcohol. You can reduce, so there are reduction reactions and no new reagents, kind of like with Grignard. But it does have nitrogen in it, and so this is actually going to reduce much like the amide. It's going to go to an amine instead of an alcohol, right? This carbon here is the carbon connected to the amine. So always make sure you're counting up your carbons. So essentially the rule is if you're doing a reduction and the functional group has nitrogen, it's going to make an amine. If it doesn't have nitrogen, it'll make an alcohol. And that is all of the reactions. I don't want to downplay it. It's a lot of reactions, but hopefully you're recognizing that there are some big groupings or families of reactions. There's a lot of similarities. So if you understand how it works, you don't have to memorize, per se, a bunch of different pictures of mechanisms. Now, there are a lot of reagents that you do need to memorize, but hopefully it's helpful, right, that so many of them you've seen before. Our reviews in some way. Synthesis is going to be part of this next test. We've gotten so many new reactions and we've added so much to our toolbox. There will be some opportunity for you to put that together to solve a more interesting problem. Your lab this week, the synthesis lab, is designed to help you with that. So you can put it off because it's not due before the exam, but I don't recommend it. You should try to work through some of it because it does pertain to this exam too. Klein is here for you in terms of strategy. I'm not going to walk through these slides because it's for you, right? It's for you for approaching how to solve problems. I love Klein's big summary flow charts. These are really useful when you're working synthesis problems on your own. And then lots of review slides here for strategies. A lot of it's focusing on, okay, this is the starting material you're allowed. This is the product you're trying to get to, right? What are some common paths, some common pieces? These last few slides are really just for you to go over. You do not have to do any more spectroscopy. We covered all the spectroscopy we're going to cover. And that's the end of chapter 20.